You watch your phone die at 10%. Not 5, not 1. The screen goes black without warning, and when you plug it back in, the battery reads 6%. There was power left. There was always power left. To you, that number in the corner of the screen is a fuel gauge. To the engineers who built it, that number is a voltage guess wearing the costume of a percentage. That guess is why people replace $1,000 phones when a $90 battery was the fix all along. Your phone does not measure the fuel in a tank. It has no dipstick reaching into the battery to read what is left. It has a chip, a tiny fuel gauge integrated circuit that watches voltage, current, temperature, and your charging history, then consults a lookup table built from lab tests on identical cells. That table is the battery's fingerprint. The percentage on your screen was never a measurement. It was always a prediction, an estimate wrapped in engineering. To understand why that estimate fails, you need to see how a lithium battery actually empties. A phone battery does not release its energy in one smooth stream from full to empty. It releases energy in two different phases. During the long middle of the discharge, the chemistry reaches a kind of equilibrium. Lithium ions shuttle from one electrode to the other at a nearly constant energy, so the voltage barely moves. When the battery is full, the voltage sits near 4.2 volts. Through most of the discharge, it drops slowly toward 3.7 volts. That is the plateau. Between 80% and 20% charge, the voltage holds almost perfectly still near 3.7 volts. Your phone leans on that flatness. It reads the voltage, compares it to the stored curve, and estimates where you are on that line, then projects where you are going. For most of the battery's life, that guess is good enough. You never notice the estimation because the road feels perfectly level. But here is the problem. The road does not stay level. Below 20%, the equilibrium breaks and the chemistry changes. The same voltage drop that once meant 5% now means 15. The meter stops being a gauge and becomes a warning light. Every percentage point below 20 hides a lie, because the voltage curve is not a slope. It is a cliff. A single tenth of a volt can represent 10% of capacity. The phone cannot know exactly where the edge is, so the meter races downward and the shutdown arrives early. That is the first thing your phone never told you. The number was always a guess, and the guess falls apart exactly where you need it most. Here is the second thing it never told you. The same phone that survives to 5% on your kitchen counter dies at 20% on a freezing street. Take that phone into the winter. The chemical reactions inside the battery slow to a crawl, and the lithium ions move through the electrolyte like traffic in a blizzard. Internal resistance climbs with every degree the temperature falls. Each demand pulls the voltage down harder and faster. So the cliff that should sit below 10% arrives at 20, sometimes 30. The cold drains the battery's power before the phone even uses it. Voltage sags under the frozen load, and the phone cannot tell the difference between empty and merely frozen. It sees the bottom of the curve and shuts down to protect the cells. The chemistry is not lying. The cold is rewriting the curve. Your phone did not lose charge. It lost the ability to deliver it. You might wonder why the phone cannot simply account for the cold. The answer is that the chip measures voltage, not chemistry. It has no thermometer buried inside the actual electrodes. It knows the temperature at the surface, but it cannot see how slowly the ions are moving through the core. It applies a standard curve to a non-standard situation. The guess becomes a lie. Here is the third thing, and it is the deepest one yet. A phone that is 2 years old dies at 30% on a warm afternoon, and the cold has nothing to do with it. Every charge cycle leaves a microscopic film on the battery's internal structures. That film is called the solid electrolyte interphase, and it is like ice building inside a freezer. It forms on the first charge, and it thickens for years while silently raising the battery's internal resistance. A fresh battery delivers smooth power. An aged one cannot. When you open the camera, the processor demands sudden energy. The old battery's voltage sags dangerously, and the phone still maps that voltage using the original discharge curve. That curve describes a battery that no longer exists. Your phone shows 20%. The chemistry says empty. The meter is not lying. It is remembering a battery that died long ago. The shutdown threshold creeps higher with every passing month. Your battery is not dying. It is being strangled by its own chemistry. The shutdown raises a sharper question. If the phone cuts off at 10%, why does it not simply drain to zero? Your phone carries a hidden buffer, a reserve of power it will never let you touch. When the meter reads zero, the battery still holds enough energy to light a small bulb for an hour. The shutdown threshold sits above the true empty point, near 3 volts. Below that line, the battery chemistry begins to break down irreversibly. Deep discharge destroys lithium cells permanently, so the phone cuts power early to protect its own future. The shutdown is not a failure. It is a mercy cut. Your phone did not lie about the 10%. It sacrificed the last drops of power to keep the battery alive. The phone kills itself to save itself. That hidden reserve is invisible, buried in the firmware, never shown on the meter. Most phones hold back a small percentage of real capacity, and when your screen reads zero, the cell is not empty. It is protected. The natural question becomes, can you fix the meter? The fix for a drifting meter is brutal and simple. Calibration does not heal the battery. It resets the software's memory of what empty means. Your fuel gauge tracks voltage against a stored curve written when the battery was new. As chemistry degrades, the curve drifts, and the gauge thinks 10% still holds real power when the cell is already gasping. Drain the phone until it dies. Charge it to full without interruption. The gauge relearns its anchors. But calibration has a limit, because a battery does not count charge cycles the way you think it does. A single charge cycle is not one drain from full to empty. It is the total energy used across many small charges. That means your daily top-ups count toward the same chemical toll. Every partial charge adds to the cycle total. The battery cannot tell the difference between one long drain and several short ones. It only measures the cumulative stress. Your charging habits today decide how many useful cycles remain tomorrow. There is one more misconception to remove. Lithium batteries have no memory effect. Older nickel-cadmium batteries forgot their full capacity if you recharged them before they were empty. That is where the old advice to drain a battery completely came from. A lithium battery does not need to be drained to remember its range. It only needs occasional calibration when the meter drifts. The old habit that helps a nickel battery can actually damage a lithium one. Draining to zero constantly pushes the cell toward the dangerous cutoff line. Heat is the real killer. Cold makes the phone shut down early, but the damage is temporary. The chemistry recovers when it warms up. Heat, on the other hand, speeds up every chemical reaction that destroys the cell. A battery that lives at high temperature ages visibly faster than one kept cool. Fast charging, hot cars, and heavy gaming all generate heat. That heat is what turns a healthy battery into one that dies at 30%. The entire mechanism closes on the only number that matters. A replacement battery costs around $90. A new phone costs over $1,000. The cost of a degraded battery is not measured in dollars alone. It is measured in the moments your phone abandons you, the navigation that vanishes mid-turn, the call that dies before goodbye, the photo that never saves. Your phone was never broken. It was just old. The meter was a guess, the voltage was the truth, and the shutdown was the only honest answer it had left. You now know the difference.